So let's start. A contour integration may be in different form. Integration of f of z dz and a path is mentioned. It may be in this form f of z dz from z1 to z2. z1 is a complex number, z2 is another complex number. It may be in another form from x1 y1 to x2 y2 f of z dz. It may be in another form f of x comma y dx plus f of x comma y. Let's say this is f1, it is f2 dy x1 y1 to x2 y2. So all the things are looking different, but actually the process of solving is same. So these four types can be the form of complex integration. So complex integration, or the common name is contour integration, is something like whatever we have done in MAT215, but we have to form this integral to either f of x dx or f of y dy, so that we can easily calculate the integral, okay, or we can easily evaluate the integral. So whatever I have discussed so far in my last consultation, that is based on linear path and non-linear path. You can have a look on that recording. But today we are going to discuss same type of integrals, but now the path that is c, or the path from z1 to z2, or from x1 y1 to x2 y2 is now a circle. So what is the procedure to solve that integral? Okay, do you understand my point?
Yes, sir.
Okay, that means we have discussed linear path and non-linear path before, but now the concept is how we can evaluate the integrals if we have a circular path. The circle may be in counterclockwise direction, it may be in clockwise direction. Besides all these formats, we may have another format, closed integral of f of z dz. Okay, so let's start contour integrals with circular path. So at first, let's take the common form of integration of f of z dz with a path c. So this time it is mentioned that where c is any random path around any circle. It may be in counterclockwise, it may be in clockwise direction. So you know that from chapter 1, whenever you have started this course, you know there is a content of region, circular region, that is annulus, disk. So that concept is again helpful here. Suppose we have modulus of z negative a is equal to r. So this equation will obviously give us a circle. So this time we have a circle. So if we have a circle, we have to understand how we can evaluate the integral. So our first process should be, we should bring this part, the inner quantity that we have, we should bring this one, z negative a equal to, actually whatever part we have inside modulus, that is a complex number. Any complex number that is in polar form can be written as r e to the power I theta. So this is the thing. You will understand again. Suppose you have a complex number z equal to r e to the power I theta. So what we will do for finding modulus, modulus of z is actually r. So if we bring the inside part, so z equal to, actually we can write r e to the power I theta. So same thing is done here. Whatever quantity we have inside modulus, if we bring it out, then it will be r e to the power I theta. That means z negative a. Here z is a complex number, a is another complex number. If we subtract these two complex number, we will get another complex number in standard form. So that will be r e to the power I theta. Okay, we have to follow some steps. So step 1, if we have, step 1 is to find the limits, finding limits of integration. So since we have theta, so theta will be, if we have a full circle and the direction is mentioned, if we have counterclockwise direction, then we will have the limit 0 to 2 pi. That means suppose we have a circle and we have counterclockwise direction. Okay, so theta is starting from 0 degree to 2 pi. So this is the limit if we have counterclockwise direction. If we have clockwise direction, that means same circle is given but the direction is clockwise. So then it will be from 2 pi to 0. So this thing is important. Now tell me, if we have just upper half circle, that is in counterclockwise direction, upper half. So for this case, what will be the limit?
So 0 to pi.
Yeah, it will be 0 to pi. So be sure that angle will be always confined in 0 to 2 pi if we have a circle, but we may have sometimes upper half circle, we may have lower half circle, we may have a circle in only in first quadrant, we may have a circle only in second quadrant or third quadrant or fourth quadrant. So depending on different shapes, we will get different limits, but the minimum value of limit will be 0, the maximum value of limit will be 2 pi. That is always same for counterclockwise direction, and for clockwise direction we will get this type 2 pi to 0. So first target is suppose done. That means we are going to find, we have found the limits, let's say. Now step 2, if you follow steps, then complex integration or contour integral will be easy. Okay, because there are so many techniques that you have to know. So that's why it's better to follow steps. So okay, step 2 is to convert this dz to d theta. Otherwise we will have problem in evaluating the integral. So how we can find d theta from dz? We can find d theta from dz by this part. You can understand that we have already found z negative a equal to r e to the power I theta. So from this part, if we need to find dz, we have to differentiate. So if we differentiate in terms of theta, we will get the result. So this thing will be done here. That means if we differentiate, or at first let's say I'm transferring a on the right side, so a plus r e to the power I theta. Now if we differentiate in terms of theta, so it will be dz, derivative of a in terms of theta is 0, and finally this part will be r I e to the power I theta d theta. So that will be the process of converting dz to d theta. You will understand again if we solve one problem. So second step is finding d theta, and step 3. This is the last step. We have to use our basic integral. That means we have to use our basic skill to find the integral. So we have integration of f of z dz. So this will be converted to f of theta d theta. And now we have to use our basic integral skill. So this is the process how we can solve complex integral. Okay, so let me take one problem here. Suppose we have to evaluate integration of conjugate of z dz, and here c is the path that is defined by modulus of z negative 2 equal to 4. So we have to evaluate this integral, and the path is mentioned. So the path is mentioned, it is in counterclockwise. So from here, if we have to solve this integral, we can use all these 3 steps. So first of all, let's try to understand what will be the limit. So since we have counterclockwise and we have the full circle, that means z negative 2 equal to 4. This is a circle. Do you understand this one? Z negative 2 equal to 4. If we input x plus yi negative 2 equal to 4, that means if we equate real part and imaginary part, so we will get from here x negative 2 squared plus y squared square root equal to 4 squared. So finally x negative 2 squared plus y squared equal to 4 squared. That is the circle with center 2 0 and radius 4. So you don't need to show all the steps because you have done all these things in chapter 1. So you have to understand that this is a circle. Is that okay?
Yes, sir.
Okay. So if we have modulus of z negative a equal to r, that will obviously be a circle always. So since it is a circle, full circle, so the limit will be 0 to 2 pi. So we are mentioning theta is equal to, theta will be from 0 to 2 pi. Now step 2. Step 2 is converting dz to d theta, this one. So here we have modulus of z negative 2 equal to 4. So what we have to do, we have to convert, we have to bring the inner quantity outside. So it will be like this. If we bring this one, so z negative 2 equal to, what will be the right hand side here? Can anyone tell me? It will be 4
4 EI.
e to the power I theta. Is that okay?
Yes, sir.
That means if we have z negative a modulus equal to r, so z negative a equal to r e to the power I theta. So this concept is important. Now what we can do, we can just transfer 2 on the right side. So we have 2 plus 4 e to the power I theta. Now we have to convert dz to d theta. So that's why we are differentiating both sides in terms of theta. So differentiation of z in terms of theta, that will be dz d theta. Differentiation of 2 is 0. 4 is constant, and you know that ddx of e to the power mx, that is equal to m e to the power mx, right? That is for real valued function. Same formula holds for complex valued function. So it will be e to the power I theta. We are differentiating in terms of theta, and I is constant, just like m is constant. So it will be I e to the power I theta. Is that okay?
Yes, sir.
So finally, we can write dz d theta equal to 4I e to the power I theta. So that is dz equal to 4I e to the power I theta d theta. This is our conversion from dz to d theta. Is that okay? So we have converted dz to d theta. Now let's move to step 3. Step 3 is to use our basic integral skill to evaluate the integral. So here we have the integral, this integration of z bar dz. So it is now, try to understand. Here we have z bar. So step 3 is to convert this given integral to f of theta d theta form, so that we can use our basic integral skill. So here we have z bar. Now try to understand, if z equal to r e to the power I theta, then its conjugate z bar will be, z conjugate will be r e to the power negative I theta, right? This is in polar form. In rectangular form, z equal to x plus yi, its conjugate will be z bar or z conjugate x negative yi. Is that okay?
Yes, sir.
So we are taking r e to the power I theta because we have circular region. So that's why this part is taken. So remember, if we have z equal to r e to the power I theta, that is in polar form, its conjugate will be r e to the power minus I theta. So this part will be r. Okay, we have already defined r here. This is r. R is 4. That means the modulus is 4. So that means it will be 4 e to the power minus I theta d z. Is that okay? We have just converted z bar. Clear?
Yes, sir.
In this part, r is 4 because from our region we can see that modulus of z negative 2 is equal to 4. So this is the modulus part. That means radius. Now let's convert dz. So here we have 4 e to the power negative I theta dz. Dz is being transferred to 4I e to the power I theta d theta. So 4I e to the power I theta d theta. Clear? We have just written the part for dz. So finally, now we can simplify. So we have 4 times 4, that is 16 is constant. We are pulling out 16 before, and we have also I is constant. So we can write 16I, 4I. So 16I is constant, and we have e to the power minus I theta and e to the power plus I theta d theta. So finally, 16I e to the power negative I theta plus I theta d theta. So we have two parts here. So that's why the powers have been summed up. So 16I e to the power 0 d theta. So 16I e to the power 0 is 1. Now, integration of 1 in terms of theta. This is the basic skill that we can apply. What will be the result for this? It will
Theta.
be theta. Now, start from the limit. So we have circular path C. Since we have the full circle, that's why the limit is 0 to 2 pi. We have already determined that in step 1. From step 1, theta is found to be 0 to 2 pi. So 0 to 2 pi, write all these things here, 0 to 2 pi, 0 to 2 pi. So now we can apply fundamental theorem of calculus. That means upper limit and negative, then lower limit. So 16i, 2 pi, negative 0. We are inputting upper limit where we have theta. And we are also inputting lower limit in the place of theta. So finally, we are getting 2 pi times 16i, that is 32 pi I. That is the result. So do you understand?
Yes, sir.
This is contour integral for circular region. So let's solve another problem. Then we will move to our next content. Okay. Let's say we have to evaluate one over z negative 2 dz around the circle z negative 1 equal to 9, and this time let's say we have clockwise direction. The direction may be defined here or it will be here. Try to have a look on the circular path. The direction may be given here also. Okay, it is a circle. Direction, if the direction is in this way, that means the orientation is looking clockwise. We have another integral. If the direction is given just like this, that means you will understand the orientation is in counterclockwise. So you have to understand, depending on the clockwise or counterclockwise region, you have to understand what will be the limit. So let me solve this one. So first of all, step 1, we have to think about the limit. So limit will be this time, since clockwise is given, so we have a circle, but the direction is like this. So it is starting from 2 pi to 0. So limit of the integral has been found here. Now is step 2. So in step 2, we have to convert dz to d theta. This is the target. So for this, we have to take the circle. So we have modulus of z negative 1 equal to 9. This is a circle. So what is the process? We have to bring the inner quantity outside. So z negative 1 equal to 9 e to the power I theta. Is that okay?
Yes, sir.
So here, what is the value of r, or let's say capital R? It is 9.
9.
That means radius is 9. Okay. Now, from here we can write z equal to 1 plus 9 e to the power I theta. So just to get d theta, we have to differentiate both sides in terms of d theta, in terms of theta. So we are differentiating So dz d theta, differentiation of 1 is 0. Okay, 9 is constant, and differentiation of e to the power I theta is I e to the power I theta. So dz equal to 9 I e to the power I theta d theta. Is that clear?
Yes, sir.
So dz is already in our hand, and let's try to convert the main integral, that is step 3. So our main integral is integration of 1 over z negative 2 dz. So here at first we have to convert this integral, that is in f of z form, it should be converted to f of theta form. Then only we can apply our basic integral skill. Okay, so that's why we are rearranging the function. So let's try to write down z negative 2, 1 over z negative 2, and dz. What is the value of dz? It is 9I e to the power I theta d theta. So for dz, we have this part. And also the limit is, this time what is the limit? 0 to 2 pi. Sorry, 2 pi to 0. So 2 pi to 0. Lower limit is 2 pi, upper limit 0. Clear? Is that okay?
Yes, sir.
Yes, sir.
Okay. Now from 2 pi to 0, 1 over z negative 2, 9I e to the power I theta d theta. So here we have z negative 2. So can you please tell me what is the function for z, or what we have found for z? We have found for z as 1 plus 9 e power I theta, right? From step 2. Have a look on step 2. We can eliminate z by 1 plus 9 e to the power I theta. Is that okay?
Yes, sir.
So this is the conversion of the main function, 1 plus 9 e to the power I theta. And we have negative 2. So this is z negative 2. So finally, we are done. Just we have to simplify this. So integration from 2 pi to 0, we are getting 9 e to the power I theta, negative 1. And here we have 9I e to the power I theta d theta. So here 9I is constant, so we can also write this one before the integral. So 9I. So finally it is looking like integration from 2 pi to 0 e to the power I theta, 9 e to the power I theta negative 1 d theta. So now we have to use our basic skill. So can you solve this one? What do we have to do now? This is going with MAT215 this time. We have to solve this integral.
Sir, we have to use U-Substitution method.
Yeah, thank you. So we can apply U-substitution. So at first, the method of U-substitution or substitution says that we have to take a suitable function for as u or z, let's say. Then we have to differentiate so that we can convert this integral to a simpler one. So this is a complicated integral now, but if we take 9 e to the power I theta negative 1 as u, so this is the substitution. Try to recall u substitution method. Whenever we are considering u, the second step will be differentiation in terms of theta, in terms of main variable theta. Okay, so here we have 9 e to the power I theta negative 1 d theta of u. We are differentiating both sides in terms of theta. 9 I e to the power I theta. If we differentiate this one, it will be this. And differentiation of 1 is 0. So we have du d theta. So 9I e to the power I theta d theta equal to du. This is U-substitution method. Now from this integral, this will be 9I integration from, oh, at the same time we have to convert the limits, right?
Yes, sir.
Or we can also keep this one. That means the limit is 2 pi to 0. 9I can be also taken here. Okay, no need to bring this 9I. Let's say it is here also. So we can see that 9I e to the power I theta d theta, that can be written as du. Is that okay?
Yes, sir.
And here we have in denominator 9 e to the power I theta negative 1, that is as u. So we have this 9I is not here. So we have actually integration from 2 pi to 0, 1 over u du. Remember, whatever limit we have, that is not for u, it is for theta. We can only apply fundamental theorem of calculus and the limits 2 pi to 0 if we have theta function. So integration of 1 over u du, that is
Log.
natural log of modulus u, right? With upper limit 0, lower limit 2 pi. So in this part, we can't input upper limit and lower limit here because these limits are for theta, but we have u. So we have to convert u to theta again. So what is u? U is 9 e to the 9 e power I theta negative 1. Upper limit 0, lower limit 2 pi. So now we can apply fundamental theorem of calculus. That is where we have theta. Theta is here. In that places, we can input upper limit and lower limit. Do you get my point?
Yes, sir.
So natural log of 9 e to the power I theta. Theta is 0. Negative 1. We are working with upper limit. Then there is a negative from fundamental theorem of calculus. Fundamental theorem of calculus is integration from a to b f of x dx, that is equal to f of b negative f of a. That means if we have the antiderivative with upper limit, lower limit, at first we have to input upper limit, then negative, then antiderivative at lower limit. So this thing we are doing here. So natural log of this part, and now again natural log of 9 e to the power I. This time theta is 2 pi negative 1. So finally we have applied fundamental theorem of calculus. Let's try to write this one. So e to the power I0, e to the power I0, that means e to the power 0, e to the power 0 is 1, so we have actually 9. So 9 negative 1 negative ln 9 e power I 2 pi. Okay, so can you remember Euler formula from chapter
Yes.
1?
Yes,
So
sir.
Euler identity, thank you. Euler identity is if we have e to the power I theta, then we can write cosine theta plus I sine theta. So we can also write this one to get the actual value. So we have e to the power I 2 pi. We can write this one as cosine 2 pi plus I sine 2 pi. And we have negative 1. Is that okay? So here we are getting natural log of 8, negative natural log 9, cosine 2 pi, cosine 360 degree is negative 1. Is that okay?
Yes, sir.
Yes, sir.
And sine 2 pi is 0. So we are getting natural log of modulus 8, negative natural log of negative 9, negative 1. So finally, negative 10. So finally, we can now remove this absolute value. It will be natural log of 8 because modulus of 8 is actually 8, and natural log of modulus of negative 10 is actually this. So this is our result. Clear? You can also
Yes, sir.
keep your answer here. That is also enough. You will get marks. But I have simplified this one. So the main idea is that whatever concept I have applied here, that is contour integral in circular region. In last consultation, I have discussed contour integration for linear and non-linear path. You can have a look here, or you can have a look on the recording. And today, I have just discussed contour integration if the path is circle. But whatever problem just we have solved here with circular path, these problems can be solved by Cauchy's residue theorem. So let's start Cauchy's residue theorem. Okay, so that means it is mentioned that use Cauchy's residue theorem. So you can't apply this process. Step 1, step 2, step 3 is not valid because already your method is mentioned. So these two things are complex integral, but it is a technique, it is another technique. So it will depend on the question. Okay, based on the question pattern, you have to answer in that way. So let's start Cauchy's residue theorem. Mathematician Augustin Louis Cauchy. Okay, so this is named after him, Cauchy's residue theorem. So by the time you know that if we have a complex valued function f of z, so we know whether it is analytic or not. We can apply Cauchy-Riemann equations, that is del u del x del v del y. Del u del y equal to negative del v del x, right? In Cauchy-Riemann equation, in Cauchy-Riemann chapter, you have learned this thing. So this is the way how we can understand whether a function is analytic or not. Okay, so now we are thinking that the function that we have, that is analytic. That means it satisfies Cauchy-Riemann equation. So after that, now we are checking another criteria. If the function is in this form, p of z, q of z, that means it is in rational form. This is called rational function. P is a polynomial function, Q is also a polynomial function. That means in numerator and denominator, we have both polynomial function of z. So f of z is now as P of z over Q of z. So this analytic function is undefined at some points. Since we have denominator, so there is a possibility of getting 0 in denominator. Let's say 1 over 0. 1 over 0, that is undefined, we know. 2 by 0, that is undefined. So we have to look for where the denominator is 0. Is that okay?
Yes, sir.
So if we solve the denominator equal to 0, then we will get some values of z. We will get some values of z. And these values will be in complex number, maybe in rectangular form, maybe in polar form. You know that? A complex number has two forms, rectangular and polar. Depending on the question pattern, we can find x plus yi, that is equal to z, or z equal to r e to the power I theta. So we may get multiple values. Let's say we are getting z equal to a, b, c. We are getting z equal to z1, z2, z3 by solving this equation. So in these points, that means any complex number is a point. That means in this point, the function will be undefined, right? Because the denominator is 0. So these points actually called singular point. So the formula for finding singular point is denominator equal to 0. Clear?
Yes, sir.
স্যার আরেকবার একটু রিপিট করতে পারবেন?
You will understand if we start one problem. Then you will gradually understand all the things. But for now, if we have a polynomial function in upper part and we have also a polynomial function in denominator, so that is in the form p by q. So every rational function, this type of functions are called rational functions. So every rational function is undefined at some points. At least there will be one discontinuity. So we have to find that undefined points. So that undefined points are called singular point in complex analysis. Do you get my point? These points are also called pole. It has another name, pole, singular point or pole. So suppose we have a function, for example, we have a function f of z equal to 1 over z negative 1. So this function is in p by q form. You can verify whether it is analytic or not. It will be analytic. But there is a point, z equal to 1. If we solve for denominator equal to 0, in denominator we can see we have z negative 1. So z negative 1 equal to 0. So z equal to 1. So now try to understand whatever I have discussed here. That is the same thing for this example. If we input z equal to 1 here, what will be the case? We will get 1 by 1 negative 1, 1 by 0. That means undefined, infinity, right?
Yes, sir.
So that means z equal to 1 is a singular point. What we may call this one, it is singular point, or we can say this is pole. Is that okay?
Yes, sir.
Yes, sir.
Because the function is a rational function, f of z is a rational function, but since it is a rational function, there is a discontinuity. So we have to find that one. And the process is this. Denominator equal to 0. Then we can solve this one, we will get the point. So this point is called a singular point or pole because if we input this point here in the main function, the function will become undefined. So let's take another function, you will understand my words. Suppose we have f of z equal to cosine pi z squared over z negative 2, z negative 3 power 10. So this is also in p by q form, but in upper part we have a trigonometric function. So we have to think about the lower part in denominator. So this is a function. We have to find the singular point. The question is find the poles. So for this, what we have to do? The formula is denominator is equal to 0. That means in denominator portion, we have this one. So z negative 2, z negative 3 power 10 equal to 0. So you know that it will be separately z negative 2 equal to 0 and z negative 3 power 10 equal to 0. So from here we are getting z equal to 2, and if we simplify this one, it will be z negative 3 equal to 0. The power 10 is not taken. That means if we simplify, we will get z negative 3 equal to 0, and finally z equal to 3. Is that okay? So
Yes, sir.
here we have found 2 points, z equal to 2, z equal to 3. These are called poles, pole 1, pole 2. Or we can say singular point. Singular point. It is singular point. So if you are asked to find the poles or singular point from a function, you have to use denominator equal to 0. So now we have found 2 points, z equal to 2, z equal to 3. You can verify if we input z equal to 2 here. So 2 negative 2 is 0. That means something by 0 is undefined, right? Similarly, if we input 3, 3 negative 2, that is 1, no problem. But 3 negative 3 is 0. So 0 times 1, 0. Something by 0 is undefined. So that's why these points are called singular point or pole. Clear? The concept of pole or singular point is important in Cauchy's residue theorem. So besides the definition of pole or singular point, we have to know what is pole of order m. Try to understand. Have you understood how we can find pole?
Yes, sir.
Okay, now try to understand what is the order of that pole. So any polynomial function, suppose we have a polynomial function x squared negative 5x plus 6 equal to 0. What we can do? We can break down this term. It is 3x negative 2x plus 6 equal to 0. X negative 3 times x negative 2 x negative 3 equal to 0. So x negative 3 x negative 2 equal to 0. So here this equation and this equation, the first one and this one are same. It is in polynomial function form, it is in quadratic form, x squared, but here we have the factors x negative 3 x negative 2. These are called factors. Is that okay? So we
Yes.
have to understand what is the power of every factor. So here we have the factor x minus 3 with power 1, x minus 2 with power 1. That means if we solve this one, finally it will be x equal to 3 and x equal to 2. So x equal to 3 is with power 1. X equal to 2 is with power 1. Or the formal way is to think about like it is x equal to 3 is of order 1. X equal to 2 is of order 1. You will understand again from the previous problems now. So order is the power of every factor. So think about this problem. How many factors we have here? 2 factors. Factor means the quantity that is inside the parenthesis. This is the first one, this is second one. So z negative 2. From z negative 2 we have found z equal to 2, right?
Yes, sir.
And from z negative 3 power 10 we have found z equal to 3. So for this example we can say f of z equal to this one has 2 poles at z equal to 2 and z equal to 3. Up to now, is that okay?
Yes, sir.
Here Z equal to 2 is a pole of order what? 1, 2, 3, 4. Which one will be?
Order 1. Sir.
Order 1. Yes, that is Z negative 2 with power 1. So that means Z equal to 2 is a pole or singular point of order 1. Clear? And Z equal to 3 is a pole of order 10. Is that okay?
Yes, sir.
So this is the pole of order m. Similarly, for this example, Z equal to 1 is a pole of order 1. Clear? So from the power of the factor, you can understand what is the order of that corresponding pole. Clear?
Yes, sir.
So now come to the basic notations. Pole of order 1 has another name that is called simple pole. Let me write again. If we have
Sir, pole is
the singular point where the function is undefined.
sir, is it the power?
Pole can be found from this equation, denominator equal to 0. So this is the way how we can find pole. Now we have to determine what is the order of that pole. But order can be defined by the power of the factor.
Okay, sir.
Okay. So here we need to understand some common notations. If we have a pole of order 1, then it is called simple pole. If we have pole of order 2, that is called double pole. If we have pole of order 3, then that is called triple pole. But if we have pole of order 4, it is written just like that. We can think about fourth pole, fifth pole, but this name are common. If we have pole of order 1, 2, 3, then simple pole, double pole, triple pole. But for the higher pole, higher orders, we can think about pole of order 4, pole of order 5. This has no specific names, but the first three has specific names that it is called simple pole, double pole, and triple pole. Is that okay? Sometimes in your question it will be mentioned that find a simple pole, find a double pole, find a triple pole. So you have to understand that simple pole means pole of order 1, double pole means pole of order 2, triple pole means pole of order 3. So why do we need pole or pole of order m? Because we are going to start Cauchy's residue theorem. And by Cauchy's residue theorem, we can solve integral f of z dz. This is our main target. So this is another new technique. So this technique is based on finding poles at first. So suppose you have pole and you have determined the pole of order m. Now the next step will be to find residue. So we have to know how to find residues. So there is a formula. Suppose a function f of z has a pole z equal to a of order m. Then we have to find the residue. So residue can be denoted in terms of r equal to residue of z equal to a. We have to find the residue of the pole. Try to understand. So this is written in mathematical way. We can explain this one as residue of z equal to a, or residue of the pole. Pole means singular point. Pole or singular point is the point where the function, where the analytic function is not defined. That means where the function is undefined. You get my point? So if we have this, the formula is, you will get the formula from your BUX videos also, but I am writing again. Limit z tends to a, then it will be 1 over m negative 1 factorial d power m negative 1 dz power m negative 1. That means we have m minus 1 derivative, m minus 1 times derivative, times z negative a power m f of z. So this is the formula. Is that okay? You have to recall this formula, or you can write this one so that we can solve any problem. This formula is important. Now suppose we have a pole of order 1. Pole of order 1. So that means pole is the part, let's say pole z equal to a, and order 1, this is the value of m. So what will be the case? Residue equal to residue of z equal to a. That means limit z tends to a, 1 over, what is the value of m now? M is 1.
So 0 factorial.
Power, yeah. So dz power 1 negative 1. I am applying this formula for this. This is one example. So z negative a power 1 f of z. So limit z tends to a, 1 over 0 factorial. You know that 0 factorial is 1. And d power 0, dz power 0. So anything power 0 is giving us 1. So that means we are getting z negative a f of z. So finally, we are getting limit z tends to a, 1 over 1 is 1, and d power 0 dz power 0, that is also 1. So that means this part is actually 1. And finally, we have z negative a f of z. So that's why this formula is for general case pole of order residue of pole of order m. But if we have to find the residue of simple pole, residue of a pole of order m, then residue will be directly, you can also remember this one, you don't need to input 1 again. So this is another formula. Now it will be limit z tends to a, the simplification part is z negative a f of z. Is that okay?
Correct.
Yeah, pole of order
Correct. Last part is order 1, right?
order 1, yeah. Or we can say residue of simple pole. You know that pole of order 1 is called simple pole. So if we have to find a residue of a simple pole, we can directly apply this formula. But if we have pole of order 2, then we can apply this, and we have to differentiate. So this is what we know about residue. And then finally, we are moving to Cauchy's residue theorem. Cauchy's residue theorem is that, let's say we are going to evaluate the integral. Our target is to find the value of this integral. That is equal to, Cauchy's residue theorem is that every integral will be equal to 2 pi I times sum of all residues. That means we can say 2 pi I. Let's say there are 3 poles. So for every pole there will be residue 1, residue 2, residue 3. So R1, R2, R3, sum of all residues, R1 plus R2 plus R3. So if we are able to find all the residues, sum all these things and multiply 2 pi I, that is the value of the integral. So I have mentioned that we have to find residues, all residues. That means if we have 3 poles, then we have to find residues of that 3 poles. But there is a condition. We will only find the residues of that pole that is inside this path. Let's say C. That is inside this path. That means the condition is here. Try to note down that find the residues. We have to find the residues for that poles only that are inside poles that are inside and on the path C. Try to understand that Cauchy's residue theorem says that you don't need to go through the proof, just try to understand the insight of that theorem. That is, we will find the residues of that poles only that is inside and on the path that is given. If a pole is outside the path, then we will ignore that one. Or we can say residue for that pole will be 0. Actually, it is not 0, there will be a residue, but we have to ignore that one. Do you understand my point? So this is the important thing of residue theorem. So try to note down this one. So now we are ready to solve one problem. So let's summarize all these things. We have a similar type of integral f of z dz with path C, or it may be in another form f of z dz. So there will be several notations. Let's say these are the 2 common notations. Okay. And this time Cauchy's residue theorem should be applied because it will be mentioned. So the formula is, Cauchy's residue theorem says that, let's say this is I equal to this integral. So I equal to 2 pi I sum of all residues. That means this one, 2 pi I sum of all residues. Or we can say 2 pi I residue 1, residue 2, residue 3, residue 4 up to residue n. Okay. So we will find only the residues that is inside and on the circle or on the path, and other poles that are outside, that will be ignored. So step 1, try to find the poles. Finding pole. And you know how we can find pole? The formula is denominator equal to 0. Is that okay? We have already discussed how to find the pole. Okay. And at the same time, in step 1, try to note down the order m for every pole. Clear? So Let's move to step 2. If you follow steps, then complex integration will be easier for you. So in step 2, we have to find the residues. So residue can be denoted in terms of R. We can say residue of Z equal to A, residue of Z equal to B, residue of Z equal to C, depending on how many poles we have. And the formula I have already mentioned. What is the formula? This one. So once we have the residues for all poles that are inside and on the circular path, then let's move to step 3. Integral f of z dz, that will be 2 pi I sum of all residues. Residue Ri, that means 2 pi I R1, R2, R3, dot, dot, dot. So these 3 steps will be followed here. Suppose we have an integration of 1 over z cube dz. Okay, let me take a complicated one so that you can understand from the very first time. So I have written here integration of cosine pi z squared over z negative 2, z negative 3 dz. Here, C is the circle, modulus of z equal to 4. So now, depending on this path, we have to evaluate this one, and remember, we have to evaluate this one by using Cauchy's residue theorem, or we can say CRT, Cauchy's residue theorem. So step 1. At first, we have to find poles. So for finding pole, the formula is denominator equal to 0. So in denominator part, we have z negative 2 and z negative 3 equal to 0, right? So we have z negative 2 equal to 0 and z negative 3 equal to 0. So it is z equal to 2 and this is z equal to 3. So besides finding pole, we have to think about the order of every poles. So what is the order of 2 and order of 3?
So 1.
1. So we can leave a comment here, that is the function f of z. Remember, this is f of z. The inside part is f of z. Okay, f of z equal to cosine pi z squared by z negative 2, z negative 3. So f of z has 2 poles, z equal to 2 and z equal to 3 of order 1, both of order 1. Is that okay? Have you understood the comment?
Yes,
Yes,
sir.
sir.
Okay, So up to now, we have found the poles. Now step 2. Step 2 is to find the residues of every poles that are inside and on C. We have to find only the residues for that poles that are inside and on the circular path, or maybe the path that we have C. So here we have the path modulus of Z equal to 4. So do you know what does it mean? Modulus of Z equal to 4, that is actually a circle. It is x squared plus y squared equal to 4 squared. It is going with your chapter 1 contents, right?
বাট স্যার এটা কিভাবে, এটা একটু বলা যায় কেন? মানে স্যার mod z equal to 4 এটা কিভাবে স্যার x square plus y square সাথে রিলেটেড?
If we have modulus of z equal to 4, then in chapter 1 you have done, wherever you have z, input x plus yi equal to 4. So if we have to remove this absolute value, then it will be square root of x squared plus y squared equal to 4. Now
Yes,
just to
sir.
remove square root, we can write x squared plus y squared equal to 4. And this is the equation of circle, because x negative 0 squared plus y negative 0 squared equal to 4 squared. Okay,
Yes, sir.
so is that okay?
Yes, sir. Perfect. Thank you, sir.
Okay, you have to understand that this is one circle with radius 4 and center at 0 0. So let's draw this one, the circle that we have with radius 4. So if we have to draw the circle with radius 4, it will be looking just like this. So this is modulus of z equal to 4. This is our path C. For now, we don't need to think about the orientation. Is it counterclockwise or is it clockwise? We are not going with that concept. This time, Cauchy's residue theorem is mentioned. So orientation doesn't matter. But we have to think, out of the poles z equal to 2 and z equal to 3, which one is lying inside and on the circle? Let's find z equal to 2, that is a point 2 plus 0 I, or we can say 2 0 point. Z equal to 3, it is 3 plus 0 I, that means 3 0 point. Is that okay? So 2 0 point 1 2, it is z1, that means z equal to 2. And z equal to 3, it is z equal to 3. Can we locate the points? Since the radius is 4, so obviously this is 4, this is 4. That means 2 and 3 are inside in this circle. Is that okay?
Yes, sir.
Okay. Since both these two poles are inside, so we can say we have to find all the residues. Residue for z equal to 2 and also residue for z equal to 3. So this time, location of the points are important. That means you have to locate the points. So here we can extend the comment that f of z equal to cosine pi z squared by z negative 2 z negative 3 has two poles of order 1 which are lying inside the circle. Let me write correctly here. So f of z has two poles at z equal to 2 and z equal to 3 of order 1 which are lying inside the circle. Clear? That means in step 2 we have to find the residues for these two poles. So now residue at z equal to 2. We can mention this one as R1, or we can also write residue at z equal to 2. It is also written in another way, residue of f of z at 2. Same meaning. Okay, don't be confused with the different notations. Meaning is same. Clear? So residue of z equal to 2. Since all these two poles are of order 1, so which formula can be applied? If we have a pole of order 1, then residue will be this. Is that okay?
Yes, sir.
So let's try to find the residue. Limit z tends to a, z minus a, f of z. So the formula will be limit z tends to a, z tends to 2, z negative a, that means z negative 2, f of z. So let's try to find this one. Limit z tends to 2. So have you understood the formula? Since it is a pole of order 1, that's why we have used this formula. Z negative 2. Now, what is f of z? F of z is this one. Can you see?
Yes, sir.
So we have to plug that function here. So z negative 2, f of z, that is cosine pi z squared by z negative 2, z negative 3. So let's simplify this one. You can see we have z negative 2, z negative 2. So similar terms can be cancelled. So finally it is giving us, that is R1 equal to limit z tends to 2, just cosine pi z squared by z negative 3. This is the simplified part from this one. Clear? Now it is a limiting problem, that is going with just limiting concept. So we have to input 2 here. If it is 0 by 0, then we have to apply L'Hopital rule, or we can apply algebraic manipulation, but it is not 0 by 0. So we can directly find a value here. So cosine pi z squared, then z is 2. So 2 squared, 2 negative 3. So that means we are getting negative 1 cosine 4 pi. So that is negative cosine 4 pi is the result for R1. Okay? We are still in step 2, because step 2 is to find, in step 2 we have to find the residues for all poles that are inside and on the circle. So since we have both points are inside, so that's why we are finding the residues for both. Now residue at z equal to 3. We have another point. কারো কি বুঝতে কষ্ট হচ্ছে?
No, sir.
ম্যাথ 215 কিন্তু একটু ঝামেলার সাবজেক্ট। সো স্টেপগুলো মনে রাখলে ফাইনালে সুবিধা হবে। আর এখন তো সুবিধাটা একটা দিক থেকে যে বাসায় বসে এক্সাম দেওয়া যাচ্ছে, সো স্টেপগুলো মনে রাখলেই কিন্তু তাড়াতাড়ি করা যাবে আর কি। আর কোথাও ভুলে গেলে দেখে নিতে পারছি।
স্যার এই কোশ্চেন স্যার এটা তো ভাষায় বসে আনসার করতে পারি না, অনেক কঠিন, একটু সহজ করে কোশ্চেন করেন।
এই স্টেপগুলো মনে রাখলে তাহলে হবে। এই যে এই প্রবলেমটাতে আমরা একটু বুঝে নেই, নেক্সট প্রবলেমে দেখা যাবে যে সবগুলো ইজিলি খুব তাড়াতাড়ি করতে পারছি। সো সিন্স ইট ইজ দ্য ভেরি বিগিনিং, সো দ্যাটস ওয়াই ইট ইজ time consuming. Okay,
স্যার 216 এ কম্পারেটিভলি সোজা স্যার, ম্যাথ 216।
216 ও কঠিন, সবাই একটা ভুল ধারণা আছে সবার মধ্যে যে 216টা কঠিন, 215টা না সরি 215টা কঠিন, 216টা ইজি, বাট অ্যাকচুয়ালি ইট ইজ নট। ওকে, 216 এও ওই ফার্স্ট পার্টটা যেটা মিডের আগে থাকে সেটা একটু ইজি থাকে, বাট মিডের পরে যেগুলো শুরু হয় সেগুলো আসলে ডিফিকাল্ট হয়। ওকে,
স্যার এটাও সেম মনে হচ্ছে,
সেম মনে
মিডের
হলেও
আগের গুলো ইজি।
if you treat it well, then it will give you the result well. Okay, so okay, let's find the residue at z equal to 3. So what is the pole of z equal to 3? Z equal to 3, what is the order of z equal to 3? It is order 1. Okay, that means the same formula can be applied. So we can say it is R2. We are mentioning R1 and R2 so that we can understand easily. So R2 equal to residue of z equal to 3. And the same formula can be applied, whatever we have applied for z equal to 2. So it will be limit z tends to 3, z negative 3, f of z. Okay, now limit z tends to 3, z negative 3, and f of z is the main function, same one, that is cosine pi z squared. By z negative 2, z negative 3. So z negative 3, z negative 3 cancelled. And the result is, that is the simplified part that we are getting, R2 equal to limit z tends to 3, it will be cosine pi z squared by z negative 2. Is that okay?
Yes, sir.
Now this is a limiting problem, we can solve this one easily. So let's input 3 where we have z. This is the position z, z. Here we have to input 3. So cosine pi 3 squared, z squared, 3 squared, 3 negative 2. So 3 negative 2 is 1. We have cosine 9 pi. So that is cosine 9 pi equal to R2. So we have found all residues R1 and R2. Let's have a look on step 3. Step 3 is saying us that the integral is equal to 2 pi I sum of all residues. If you have two residues, then R1 plus R2 times 2 pi. Done. So finally, result. Integration of the main function f of z. So we don't need to write again. Integration of f of z dz. F of z is the big one, cosine pi z squared by z negative 2, z negative 3. Try to understand. So that is equal to 2 pi I sum of all residues. So how many residues we have here?
2.
2. So this is step 3. So that means 2 pi I sum of R1 and R2. So it is our result. That is just input R1. R1 is negative cosine 4 pi. Yeah, it is negative cosine 4 pi plus R2 is positive cosine 9 pi. If you have calculator, you can find the value. But this is enough answer. Yeah.
স্যার ওখানে একটা লেখা ছিল যে একটা কন্ডিশন ছিল স্যার যে রেসিডিউ গুলো ইনসাইড সি এর মধ্যে হওয়া লাগবে।
I am taking one problem, let's say. Now you will understand. So have you understood the basic concept of Cauchy's residue theorem here?
ইয়েস স্যার।
Yes, sir. Yes,
Okay.
sir.
Let's say we have to evaluate one integral 1 over z squared plus 4 dz. The path C, let's say C is the contour that is defined by modulus of z plus 2I equal to 1. C is the contour that is defined by this circle. So we have to evaluate this integral, and it is mentioned that evaluate this integral by Cauchy's residue theorem, that is CRT. So first of all, you can think about this is a contour. So if Cauchy's residue theorem is not mentioned, you can apply your previous technique. But since Cauchy's residue theorem is mentioned, so there is no alternative way. So we have to apply Cauchy's residue theorem here. So step 1. Can anyone please tell me what is the step 1?
We have to find the poles by
Yeah,
taking
we have to
denominator
find
0.
the poles. So finding poles is our first target. So poles can be found by considering denominator equal to 0. So in denominator, we have z squared plus 4 equal to 0. That means z squared equal to negative 4. So z equal to plus minus root over negative 4. So z equal to plus minus root over 4 root over negative 1. So we have z equal to plus minus 2I. So how many poles we have found? We have found actually 2 poles, z equal to, so poles are z equal to 2I and z equal to negative 2I. Clear?
Yes, sir.
Also, in step 1, it is mentioned that try to note down the order of every poles. So we have to find the orders also. Now, you can see that the denominator function is not in factored form. Clear? If we have the factor, we can easily understand if the factor with power 1, order will be 1. If the factor with power 2, order will be 2. Is that okay?
Yes, sir. Yes, sir.
So
Yes, sir.
can anyone understand that what will be the pole for these 2 poles? Sorry, what will be the order for these 2 poles? Any idea?
2.
Sir,
Okay, actually not 2, not 3. It will be 1. Try to understand by this way. That is x squared negative 5x plus 6 equal to 0. If we have this function and you know that the result will be x equal to 2, x equal to 3, right?
Yes, sir.
So x equal to 2 and x equal to 3 will be the result. But what will be the previous line from the result? It will be x negative 2 equal to 0, x negative 3 equal to 0. And if we take another previous line, it will be x negative 2, x negative 3 equal to 0. That means this part is same as this one. Is that okay?
Yes, sir.
So what we can do, z equal to 2i, we are here, z equal to negative 2i. So let's take a previous part. So it will be z negative 2i equal to 0. It will be z positive 2i equal to 0. Is that okay?
yes, sir.
And these two are coming from, if we take another previous part, it will be z negative 2i times z positive 2i equal to 0. If we multiply these two, then only it is possible to get this z squared plus 4 equal to 0. You can verify. Same result you will get. Do you understand my point?
Yes, sir.
Yes,
So
sir.
that means
Yes, sir.
the denominator that we have here, that is not in factored form, but we can write this one in factored form because factor form is important. So z squared plus 4 is actually z negative 2i times z positive 2i. So we can write again the main function or main integral so that you can understand easily. Actually, we have 1 over z negative 2i z positive 2i dz. Instead of this, we are writing this one. Do you understand my point?
Yes,
Yes.
sir.
Now tell me, what is the order for these two poles?
One.
1. So both poles are with order 1. So here we have order 1, order 1. Okay? And the function that we have, this is the main function. Let me write the function f of z equal to 1 over z negative 2i and z positive 2i has two poles at z equal to 2i and at z equal to negative 2i, has two poles of order 1. Or we can also write in alternative way, instead of writing this one, we can write f of z has two simple poles. Can you write this one? Because pole
Yes,
of
sir.
order 1 is known as simple pole.
Yes, sir.
So we can use any of the notations. So f of z, this is our comment, that f of z has two poles at z equal to 2i and z equal to negative 2i. Both are of order 1. You don't need to write all these things. You can solve directly. But for better understanding, I am writing. Okay. Now step 2. Step 2 is to draw the region. And we have to understand out of these two poles, which are inside and on. And we have to check, is there any pole which is outside? So we have the region, this. That is modulus of z plus 2i equal to 1. So we can apply our previous concept where we have z, we can input x plus yi. This is a circle, but we are trying to understand where the center and where the radius, what is the radius. So x plus y plus 2i equal to 1. And just to remove this absolute value, we will have a square root of x squared y plus 2 squared equal to 1 squared. Equal
স্যার
to,
হোয়াট ইফ যদি
yeah,
দুইটার অর্ডার সেম না হইতো?
order. Let's say this is order 1, this is order 2. Then for this pole, we will apply residue for this formula will be applied. This one. And if we have pole of order 2, if we have pole of order 2, then we have to apply this one where m will be 2. Okay.
ওকে স্যার।
Okay. So from here we can see x squared plus y plus 2 squared equal to 1 squared. We are taking a square on both sides. Finally, you can understand that we have x negative 0 squared plus y negative 2 squared equal to 1 squared. What is the center?
0, 2.
0, negative 2.
Negative 2, yes.
And radius? Radius is 1. Okay. So let's draw the figure. Because in Cauchy's residue theorem, figure is important. So at first 0, negative 2 should be located. So 0, negative 1, negative 2. This is our center. 0, negative 2. What is the radius? Radius is 1. So this distance is 1. Is that okay?
Yes, sir.
Yes, sir.
Same distance will be taken here, here, here. So we have the circle. The circle will look like this with radius 1. So this is modulus of z plus 2i equal to 1. So just to have the center and radius, we have explained all these things. So now let's try to check out of these two poles, z equal to 2i and z equal to negative 2i, which one is inside and which one is outside. So z equal to 2i can be written as 0 plus 2i, right?
Yes, sir.
So 0 plus
Yes, sir.
2i is a point 02. Are you sure?
Yes, sir.
Yes, sir.
Now tell me, 02 is located here or where?
Sir, upwards, sir, not inside the
Upward.
cell.
So
Yes, sir.
02. We can mention this is Z1, this is Z2. So Z1 is here. That means
So it
2,
won't be taken, right?
yeah, it should be ignored because Cauchy's residue theorem says that if we have a pole that is outside the region, that should be ignored. So we don't need to find a residue for that pole. And let's think about another point. We have another one. So this is outside. This one, Z2 equal to negative 2i. So that means 0, negative 2i. So 0, negative 2 is the point. So 0, negative 2, the center is coming, right? That means Z2 is inside.
Yes, sir.
Yes, sir.
Clear? So we just have to find the residue for Z2. So we can leave a comment again. Z1 equal to 2i is outside of C. Z2 equal to negative 2i is inside. Okay, so we don't need to find the residue for this one. Let's say R1 is ignored 0. It is actually not 0, so we don't need to write this one. That means we are ignoring this. And we have to just find this. Okay, let's say R1 is ignored. That means 0. And R2, we have to find R2. Or since we have only one pole inside, we can just mention this is R1. Clear?
Yes, sir.
Yes, sir.
So we are mentioning the pole that is inside, its residue will be R1. Okay. So residue at Z equal to negative 2i, that can be denoted as R1 equal to residue of f of z at z equal to negative 2i. Since it is pole of order 1, so we can apply this formula, that is limit z tends to a, z negative a, f of z, if we have residue z equal to a. So it will be limit z tends to negative 2i, z negative, try to understand, z negative a, this is our a, so be careful, z negative a, and a is this one. Is that okay?
Yes, sir.
Okay, so finally what we are getting, limit z negative negative 2i, z tends to negative 2i, and the simplified part will be z plus 2i f of z. Now plug the function. What is our function?
So z
1 by
square plus
z
4.
negative 2i, z positive 2i. Is that okay?
Yes, sir.
So 1 by z negative 2i, z positive 2i. Now we can see that the beauty of Cauchy's residue theorem is that some parts will be cancelled and you will get a simplified or reduced term. Okay, so what we are getting here, so R1 equal to limit z tends to negative 2i, 1 over z negative 2, z negative 2i. So let's input z here. This is just a simple limiting problem. So 1 by negative 2i, negative 2i. In the place of z, we are just plugging negative 2i. So it is 1 over negative 4i. That is R1. We can also simplify this part to standard form, a plus bi, but no need. Okay, finally, step 1, step 2 is done. Now step 3. Can you remember step 3?
Yes, sir, we have to multiply with 2 pi I and
Yeah.
sum of all the residues.
So total result of that integral will be 2 pi I. So R1 equal to negative 1 over 4i. So this time we can simplify that I will be cancelled. So we have 2 pi by negative 4. What will be the result? Pi by 2, right?
Yes, sir.
So this is our result. This is the result for this integral. So Cauchy's residue theorem is important. Why it is important? You will understand now. Here you can see we have improper integral. For solving improper integral, we need Cauchy's residue theorem. So this thing is important. I have seen some videos in BUX, that is, there are some problems in week 8 that are based on improper integrals. Okay, so you have to also go through improper integral. So let's take one problem from improper integral so that you can understand the application of Cauchy's residue theorem. So that means now we are going to see how Cauchy's residue theorem can be applied to solve improper integrals. In MAT215, you have learned how to solve improper integral. So same problem can be solved by contour integral also. So let's say we have one integration that is from negative infinity to positive infinity, f of x dx. You will get to know this thing in MAT220. Okay, the definition of improper integral is there. Improper integrals are the integrals with a to infinity f of x dx, with negative infinity to b f of x dx. It may be negative infinity to infinity f of x dx. So that means if we have lower limit as negative infinity, upper limit as infinity, both lower and upper limits are infinity, that integrals are called improper integrals. Okay, do you understand my point?
Yes, sir.
Okay, so you can see that we have f of x, not f of z. Try to focus on here, f of x. So that means that is going with real valued function, not complex valued. Clear?
Yes, sir.
But just to solve this one, we can also apply contour integral technique. We can also apply Cauchy's residue theorem. Or we can also apply the method that you have learned in MAT220. But since you are in advanced level, you have to also understand how we can apply Cauchy's residue theorem in solving improper integrals. Okay, so let's say we have a function that is of 1 over x squared plus 4 dx, negative infinity to positive infinity. So how we can solve this one? Let's try to understand. From your BUX video, you will get one verification for this improper integral. Try to go through that. If you have this integral, so since we have negative infinity to positive infinity, that is a big thing. Okay, that means we have unbounded region, but we can think about an upper circle that is coming from negative infinity to positive infinity. Okay, we have a circle, let's say we have an upper circle that is a contour that is coming from negative infinity to positive infinity. So now there will be a question why we are taking upper circle instead of a circle.
Yes, sir.
So the answer can be given in this way, that instead of infinity, let's say r is going to infinity. That means r is approaching to infinity. So r, negative r, positive r, and it is also r. So negative r is a complex number, positive r is also a complex number. So negative r can be written as r negative r plus 0 I, positive r can be written as positive r plus 0 I. So negative r0, positive r0. So that means this is negative r0 point, this is positive r0 point. Now we can understand that we have to integrate from negative r to positive r. So that means we can think about an upper circle. Do you understand my point? And we can extend our idea to infinity. R is thought to be infinity. So this is why we are taking upper circle. This is the short overview. We have a real valued function, but with the help of complex valued function, we can solve that improper integral. So here, the function that we have f of x, corresponding complex valued function will be f of z. So instead of this integral, we can think about one integral f of z dz. Here we have f of x dx, we are thinking about f of z dz. I am repeating that if we have integration f of x dx, we are taking integration f of z dz. Do you get my point?
Yes, sir.
Okay, this is a contour. See, this is equal to f of x dx from negative r to positive r. And we are mentioning that r is going to infinity, then and this one is same. But besides this, we have another part that is called Jordan lemma. So besides this one, we have integration of f of z dz in a small contour. But if you watch a video in BUX, you will see that this part is 0. There is a theorem there. Okay, try to go through that one. I am not repeating that. So it will be 0 for improper integrals. That means if we have negative infinity to positive infinity f of x dx, we want to evaluate the integral, this improper integral. This can be done by this way: f of z dz with a big contour that is from negative infinity to positive infinity. That is equal to negative r to positive r, f of x dx, plus a small contour cr with f of z dz. This is actually called Jordan lemma, and this will give you 0. So for this part, you can obviously write 0. So you don't need to show this part. You can easily skip this one because we have a theorem. Using that theorem, you can write this is 0. So finally, f of z dz, that is negative r to r f of x dx. That means here we can introduce limit r tends to infinity, limit r tends to infinity. So that means minus infinity to infinity f of x dx, that will be same as f of z dz over this contour. So that means for solving this improper integral, we need contour integration. Is that okay?
Yes, sir.
So this is the theoretical part. So let's solve this integral, whatever I have written here. You will understand now. And then Cauchy's residue theorem will be again applied. So evaluate negative infinity to positive infinity, 1 over x square plus 4 dx. by using Cauchy's residue theorem. Clear? So can you please tell me what is the main function here? Here f of x is equal to 1 over x squared plus 4. It's quite difficult to understand the theoretical part, but actually if we have a look on problem solving, then you will understand the process. Its corresponding function f of z will be 1 over z squared plus 4. Is that okay?
Yes, sir.
Okay. Now it is our formula. This is the formula for solving improper integral. So using this formula, we can write this expression. So we are thinking about negative infinity to positive infinity. So since infinity is unbounded region, so we can think about negative r to positive r. That means from negative r to positive r, we have an upper circle. So we have an upper circle with radius r. And remember, r is going to infinity. So let's try to write by this way. The formula says that the contour f of z dz is actually negative infinity to positive infinity, or we can write by this way: limit r tends to infinity, negative r to positive r, f of x dx plus a small contour. We are mentioning CR, f of z dz. This is the formula. So with Cauchy's residue theorem, this is an extension. Is that okay?
Yes, sir.
Okay. So let's write this. We have a contour C, f of z. So f of z is 1 over z squared plus 4, and we have dz equal to limit r tends to infinity, negative r to positive r. So r tends to infinity, negative r to positive r, it is actually this one. So same meaning. So here we have f of x, write down f of x. F of x is x squared plus 4 dx. We are supposing that we have a small contour. This is the total contour C. This is a big region, but inside this region, we are assuming a small contour CR. Compared to this big region, this small region can be ignored. So that's why this part is 0. Okay? But first of all, we should write clearly. So z squared plus 4, this is f of z, and we have dz. So this is called Jordan lemma. By Jordan lemma, we can write this is 0. 1 over z squared plus 4 dz c. That means limit r tends to infinity, negative r to positive r, 1 over x squared plus 4 dx. And this part is 0. So we don't need to write this one. That means actually what we can write, this is also same as, this one can be also written as negative infinity to positive infinity, 1 over x squared plus 4 dx. So can you see, this is our main integral I.
Yes, sir.
So just to find I, what should we do? We don't need to focus on right side, we have to focus on left side. Clear?
Yes, sir.
So just to solve this one, we know we have what we have to do, that is Cauchy's residue theorem. So I equal to C 1 over z squared plus 4 dz. This time there is no information given for C, but since -infinity to infinity is given, so we are mentioning that C is an upper circle. Clear?
Yes, sir.
Okay, so how we can solve this one? By using Cauchy's residue theorem. Clear?
Yes.
And let's mention where C is a circle, where C is an upper circle from -r to r. So just recall all the steps that you have learned in Cauchy's residue theorem, step 1, step 2, step 3. What is step 1?
We have to find the poles.
We have to find the poles. Okay. At the same time, you can have a look here that it is z square plus 4. So z square plus 4, is it in factor form?
No, sir.
No. So that means we can bring the factor form.
ডিনোমিনেটর ইকুয়াল টু 0 করতে হবে না, মানে
Yeah, yeah.
আগে যেরকম করলাম z
Yeah.
স্কয়ার প্লাস 4 ইকুয়াল টু 0।
Yeah, sure. So step 1. So z square plus 4 equal to 0. Step 1 is to find poles. So it will be finally z equal to plus 2i, negative 2i, right?
Yes, sir.
But the previous term that will be here, it will be z negative 2i, z positive 2i equal to 0. Is that okay?
Yes, sir.
Yes,
So
sir.
this is same as, so 1 over z negative 2i, z positive 2i dz. Is that okay?
Yes, sir.
So just we have rearranged the function in factored form. So step 2.
Sir.
হ্যাঁ,
স্যার z টু দি পাওয়ার 4 থাকলে তো পাওয়ারটা 2 হয়ে যেতে পারে না স্যার, মানে যেটা
yeah.
বললেন আর কি।
Then it will be squared, okay?
Yes, sir. পাওয়ার হচ্ছে, yes.
You got the right thing, okay. So step 2 is to check which poles are inside and on the upper circle and which is not. At the same time, we have to find the residues. But before that, let's find the order. So we can say f of z, that means this function has 2 poles at z equal to 2i and at z equal to negative 2i. Both are of order 1. Is that okay?
Yes, sir.
Yes, sir.
So the value of m is 1. So now think about the upper circle, that is from negative r to positive r. In Argand diagram, we are drawing a circle from negative r to positive r. So since it is of radius r, so it will be also r. Now we have total 2 points, z equal to 2i, z equal to negative 2i. We have to check which points or which poles are inside and on which is outside. So can you understand the difference between inside and on? I'm repeating several times inside and on. We are sure that what is inside. Inside means this part. On means
Exactly.
On the boundary line. Boundary line, right? Yes.
boundary. Yeah. If it is on the boundary, if the pole is on the boundary, then we have to also find the residue. Okay. So we have z equal to 2i and z equal to negative 2i. So z equal to 2i is actually 0 plus 2i, that means 0 to I. So 0 to I, you can think about infinity, since R is infinity, so 0 2 is obviously here, 0 to I, right?
Yes, sir.
Yes, sir.
It is unbounded radius. That means it may be 100, it may be 200, but 0 to I is obviously lying in this region, in this upper circle. Is that okay? Have
Yes,
you got the concept? Okay. Z equal to negative 2I. That means 0, negative 2I. That is 0, negative 2I. So it is here. So which one should be taken?
So
Z equals to 2i.
2i.
So this will be taken, but it is outside. So it is inside and it is outside. So
স্যার এটা একটু ক্লিয়ার করা যাবে যে আপনার নিচের সার্কেলটা কেন নিয়ে নেই আমরা?
if a contour is coming from Z1 to Z2, that will be a circle from Z1 to Z2. This is an upper circle. So that's why we are using that concept. So
Okay, sir.
now think about a big region. Instead of negative 2, suppose you have negative 100 to positive 100, negative 1000, 10,000 to 10,000. So negative R to positive R, that will be an upper circle. So that's why we are taking upper circle. So for improper integral, always you have to understand that you should take upper circle. Clear? Since Z equal to 2I is inside the upper circle, we have to find the residue. So we can leave a comment here so that you can understand. F of Z has 2 poles. Now I am writing 2 simple poles. That means pole of order 1. F of Z has 2 simple poles at Z equal to 2I and at Z equal to negative 2I. But only Z equal to 2I is lying inside the contour C. Clear?
Yes, sir.
So since it is inside, so we have to find the residue. So how many residues there will be? Only one.
One residue.
One
Only
residue.
one.
Let's say it is R1. So residue at Z equal to 2I. We are mentioning it is R1. R1 equal to residue at Z equal to 2I. So limit Z tends to A. A means to I. Z negative to I. F of Z. And you know, the process is now very simple. Limit Z tends to 2I, Z negative to I. What is our main function? Main function is 1 over Z negative 2I, Z positive 2I. Z negative 2I, Z positive 2I. So we can now cancel the similar terms. R1 is equal to limit Z tends to 2I, 1 over Z plus 2I. So this is a limiting problem. We can input 2I. So 2I plus 2I, that is 1 over 4I. This is R1. So finally, our residue is in our hand. So step 3. We can move to step 3. What is step 3? Step 3 is integration of f of z dz, that is equal to 2 pi I sum of residues. Since we have only one residue, so R1. So 2 pi I 1 over residue 1 is equal to 1 over 4I. Simplification part will be pi over 2. Is that okay?
Sir,
Yeah.
Sir, the step 3 integration, sir, will that also remain for half circle as well?
A circle is not the appropriate word. It is for contour. The contour may be full circle, it may be half circle, it may be a circle in first quadrant, it may be a different shape like this. Okay, that means the poles are here. So you will get this type of problem in your reference book. That means Cauchy's residue theorem can be applied for any contour. So step 3 is done. We have found pi by 2. That means, can you understand that from where we have started? This one, 1 over z square plus 4 dz, that is equal to the main improper integral. So we can use one equation number here. This part is becoming pi by 2. So that is the result for the right side. Negative infinity, positive infinity, 1 over x squared plus 4 dx, that is equal to. Okay, let's try to verify whether our result is correct or not. So okay, I am concluding the session here. Okay.
Okay.
From negative infinity to positive infinity. You have done Mathematica in MAT215.
Yes, sir.
So I'm using Mathematica here. Pi by 2. Can you see?
Yes, sir.
Okay. So we are able to solve this improper integral by using Cauchy's residue theorem. So the formula that is here, if you have improper integral, you have to apply this formula. That means you are converting that improper integral in this way. So okay. Thank you for joining the session. Best of luck.